Welcome to Cause Before Symptom, uncovering the real cabal and spiritual forces that are controlling the world. And now, here is your host, James Carter.
Welcome to Cause Before Symptom. I'm your host, James Carter, and today is July 2nd, 2026. Tonight's episode is all about, did CERN break reality? The physics behind the timeline theory. So good evening, everybody. Welcome back to Cause Before Symptom, where we don't chase headlines, we chase causes. And tonight we're stepping into one of the most controversial conversations on the internet. Some people believe CERN, home to the world's largest particle accelerator, accidentally changed reality itself. Others insist the idea is complete nonsense. No different than science fiction. Now, between those two extremes lies a question that deserves something far better than ridicule or blind acceptance. It deserves an honest investigation, which is something I'm really good at. And the story usually begins in 2012. Remember, the Mayan calendar said the end of the world will be in 2012. How could they have predicted that we could build CERN by then? Well, CERN announced the discovery of the Higgs boson, a particle that physicists had spent decades searching for. It was a historic achievement and one that confirmed an important part of the standard model of particle physics. But around the same time, another story began spreading online. People claimed they remembered events differently than history recorded them. Logos appeared to have changed. Famous quotations seemed different. Geography looked unfamiliar. These collective memories eventually became known as the Mandela Effect. And before long, many people connected those memories to CERN's experiments. And one explanation spread further than any of the others. And according to this story, when CERN smashed protons together at an unprecedented energy level, something unexpected happened. A proton was supposedly pushed out of its proper place in space-time. Reality apparently shifted, and humanity unknowingly entered another timeline. Now, some versions say history itself changed. Others suggest that two realities merged together. Still, others argue that CERN weakened the boundary between parallel worlds. It's a fascinating story, but there is one big problem. Almost no one begins by asking whether modern physics even contains a mechanism capable of describing such an event. Meaning, can it be calculable? Well, that's where tonight's investigation begins. Instead of asking whether the theory is true or false, we're going to ask whether the language being used even matches the language of physics. What exactly is a timeline? Is it the same thing as space-time? Is it the same thing as what physicists call a branch? And we'll be talking about branches more tonight. Does quantum mechanics actually describe multiple realities, or is that simply one interpretation among several? Well, these questions matter because words have precise meanings in science, and two people can use the same word while describing completely different ideas. And without even realizing it, they end up arguing past one another. Over the past several days, I've been gathering as many books as I can across the entire scientific spectrum. They're out there. You can get them. And I am really good at finding books. Not books that begin with the conclusion that CERN broke reality, and not books that dismiss the discussion before it even begins. Instead, I wanted the strongest voices from modern physics itself. Not all of them could be satanic and after, bringing in the Antichrist, all right? We looked at particle physics, quantum mechanics, cosmology, quantum gravity, and one of the most respected modern defenses of the Everett interpretation. We're talking about that. Often called the many worlds interpretation. Now, my goal was simple. If there is a path from accepted physics to the CERN timeline theory, we should be able to find it. If there isn't, we should understand exactly where that path breaks down. Because people are freaking out. And I'm telling you, people really believe that CERN is playing around with the timelines or changing history, or they think it's some time travel mechanism. But what surprised me the most was not what I found, but what I didn't find. I found serious physicists discussing branching histories, decoherence, never even heard of that before, quantum states, extra dimensions, and the structure of space-time. I found vigorous debates over the meaning of quantum mechanics that have continued for nearly a century. I found genuine disagreements among brilliant scientists about what reality ultimately looks like beneath the mathematics. And what I did not find was a published physical mechanism describing how a proton, one particle of light, could simply be knocked out of our timeline in the way that the internet often describes it. Now, that doesn't automatically make the idea impossible, as we're going to discover all about it. It means that we first have to define what such a statement would physically mean before we can test it against evidence. And that distinction may sound small, but it changes everything. Throughout history, scientific progress has often come from asking better questions rather than demanding immediate answers. Einstein didn't begin by asking whether time could slow down. He asked what would happen if the speed of light were always constant, which nobody was thinking of that time. That's, wow, I never even thought about that. Quantum mechanics didn't begin by proposing multiple worlds. It didn't. This is something new that's come out in the last 20, 30 years. Quantum mechanics began by trying to explain experiments that classical physics just could not. And every major breakthrough started by carefully defining the problem before proposing a solution. And that is exactly what we intend to do tonight. Now, as we move through this investigation, you may discover that the internet has blended together several completely different ideas. The concept of alternative timelines, the many worlds interpretation, parallel universes, extra dimensions, decoherence, and the Mandela Effect are often spoken about as though they are interchangeable. Well, they're not. Some belong to unresolved scientific debate, others remain entirely speculative. Our task tonight is to separate those ideas without stripping away the wonder that inspired the question in the first place. We're not going to point fingers and say they're wrong. We're going to throw the evidence that we could find through modern physics and quantum mechanics, blend them together and try to figure out the most common answer to the problem. Now, this is not an episode about proving CERN innocent either. Okay, they've done some weird shit around their facility. And it's not an episode about proving the timeline theory correct. No. It's an episode about learning how to think carefully when extraordinary claims collide with extraordinary science. I don't want your hearts to race every time you doom scroll and someone says, CERN opened up a timeline and the demons are coming out. Slow down, mister. This is an episode learning how to think carefully. If modern physics points toward possibilities stranger than we have imagined, we should not fear them. If it rules out certain ideas, we should be willing to accept that as well. So truth has nothing to fear from this investigation. And so tonight we begin where every good investigator begins, not with certainty, but with simple curiosity, as I'm curious. We're going to open the doors of CERN. We're going to step inside the most powerful particle accelerator known to man. And we're going to ask a question that millions of people have wondered far more than a decade. The question is simple. Did CERN really change reality? Or have we misunderstood both physics and the mystery itself? It's going to be a great show. I'm excited about it. Shout out to everybody on the live chat Rumble. Number one warrior is Scorpion. Scorpion says, hey, Pastor and Warrior family, excited for tonight's show. Scorpion, thank you for being here. Guys, let's get straight into breaking news.
Welcome to Shitty Breaking News with your host, James Carner, offering his shitty opinion.
Yes. So Trump made more than $1 billion from his cryptocurrencies. And people are pissed. Well, look at Congress. How come Congress is, betting on horse races and getting away with it? How extreme heat is changing DC's July 4th weekend plans. Oh, extreme heat. I love this whole new concept called a heat dome. We're all in a heat dome, especially Portland. They're saying we're all going to die. Yeah. In Oregon, they are claiming that we're going to all die. All right. And they're pushing and pushing and pushing this climate change bullshit. Now, climate always changes. It does. It's changed even before man came into the picture. Climate changes. All right. Quit trying to follow the idea that we're all going to die. Fear is what keeps you paying your taxes. Fear is what keeps you connected to the world, because the world is run on fear. If you really, truly trust in God and love Jesus as your Lord and Savior, the Bible says, stop worrying about all that crap. That's not for you to worry. You're just an ambassador representing the kingdom of heaven. Right? What to know about the Society of St. Pius X, the schismatic group that's now coming out. Who cares? Trump administration indicts Olympic athlete for reflecting pool vandalism. Well, when you act out in extremism, you get extreme consequences. Russian attacks kill at least 25 injuries scores in Kyiv after Zelensky warned of who gives a shit. It's a war. We don't know what's really going on. You know, Russia, are they profiting off of it? No, it's weakening Russia. Is America profiting off of it? Absolutely, as Ukraine is one of our biggest buyers of weapons. Well, apparently the Onion's new parody of Alex Jones's InfoWars, it starts with $100,000 to Sandy Hook families. Oh my God. The satire news site, The Onion, isn't waiting to take possession of InfoWars to launch a parody of Alex Jones's conspiracy platform. So more than a year after first trying to buy InfoWars, The Onion on Thursday will debut a send-up under its own website with plans to give some of the revenue to families of the victims in Sandy Hook Elementary School shooting. Man, I just using humor, because that's all The Onion is, humor. Trying to buy it out. I think this is all just like evil. It just feels evil, right? A satire news website, The Onion. They wanted to buy it. That's just evil. And then now they want to, we want to give money to the Sandy Hook families through satire. I don't know. Something just stinks to high heaven here. And that's pretty much the world we live in. It's a fallen world. Chill out, honey bunny. All right, when we come back after a short commercial, we're going to talk about CERN. The story everyone thinks that they know, right? Did CERN break reality? What are the physics behind the timeline theory? Well, we're going to go through all of it right away.
Every year, millions of Americans sign a contract they don't even know exists. They think it's just another tax return, but that signature means something far deeper. It starts with that first job at 16. The system takes a piece of her check, then promises to give some back if she signs the return. Every April 15th, the same cycle repeats, not by law, but by belief. The system didn't bind them, their own signature did. Learn the truth at unincorporatedassociations.com.
All right, did CERN break reality? Are we living in a new timeline? Are the physics behind the timeline theory correct? Well, we're going to be exploring that tonight. So, the story everyone thinks that they know is CERN screwed with our timeline. And now we're all living in a multiverse, and we popped over to another one while the other timeline that we were living in exploded, apparently. Well, on July 4th, 2012, scientists gathered at CERN with an excitement that had been building for decades. The announcement they were about to make would become one of the most defining scientific moments of the 21st century. Researchers working at the Large Hadron Collider revealed that they had discovered a new particle whose properties closely matched those predicted for the Higgs boson. Now, newspapers around the world celebrated the achievement. Television networks declared that physicists had found the so-called God particle, the Higgs boson. a nickname many scientists disliked because it oversimplified the discovery, and for the scientific community, it was a tremendous victory. It confirmed a missing piece of the Standard Model, the mathematical framework that describes the known fundamental particles and forces of nature. Now, to understand why this mattered, imagine trying to complete a 1,000-piece puzzle with a one piece missing, and every other piece fits perfectly, but without that final piece, you can never be completely certain the picture is correct. Well, for nearly 50 years, physicists believed the Higgs boson was that missing piece. They had built theories around its existence, but no one had ever observed it directly. Well, the Large Hadron Collider was designed in part to search for evidence that this elusive particle truly existed. And when the evidence finally appeared, it was not simply another scientific paper. It represented the confirmation of decades of predictions, calculations, engineering, and international cooperation, meaning they spent billions building this thing. And for most of the world, the story ended there. Scientists celebrated. Universities published articles explaining the importance of the discovery. The public moved on to the next headline. And yet outside the world of physics, another narrative quietly began to grow. It did not begin inside laboratories or academic journals. It began on internet forums, social media, podcasts, and YouTube channels, where people started asking a very different question. What if CERN had done more than discover a particle? What if something unexpected had happened during those incredibly energetic collisions? What if reality itself had changed? Well, at first, conversations were scattered and disconnected. Some people noticed that famous movie quotes did not match the way that they remembered them. Others believed company logos had changed over time, and still others insisted they remembered historical events differently than the official record. Now, many of these observations eventually became grouped together under a single label, the Mandela Effect, right? Well, the same came from people who believed that they remembered Nelson Mandela dying in prison years before he actually passed away in 2013, which I remember. Whether these memories resulted from normal human memory, social influence, or something more mysterious became the center of an ongoing debate. Now, I do remember watching Tommy Boy when he saw in his own office playing, and he was with the fan, and he was speaking into the fan. He's like, loo, 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 la, la, la. Then he goes, Luke, I am your father. Okay? And I remember the original, where Darth Vader said, no, I am your father. But Tommy Boy said, Luke, I am your father. And then he says, no, I am. So basically, could we have just remembered it wrong because we watched another famous movie? Everybody saw that movie, and then they just remembered it that way? It could be. We don't know. But as the Mandela Effect gained popularity, people naturally began searching for explanations, like what happened to the cornucopia that was in the Fruit of a Loom logo. Surfer Wife is here, says, hey, been a while. Missed you guys. Hope everyone's well. Thank you for being here. Pray for Boots. Boots' wife had a stroke, and she's recovering from it, and I think she's going to be fine, but please pray for Boots' wife. Boots is one of our regulars here. Cognitive psychologists have spent decades demonstrating that memories are reconstructed rather than replayed like a video recording. And under the right conditions, groups of people can confidently remember details that never actually occurred. This explanation has considerable scientific support and accounts for many well-documented cases of false memory. I also remember the Zapruder film of the JFK assassination. I remember there was only 4 people in a limo, and now there's 6. Yet for many people, it did not fully explain the personal certainty that they felt about particular memories, right? I also remember the moon not in its crescents being this just normal this way, you know, up and down instead of, all the way down like this now. But hey, we could be remembering it wrong. I don't know. So others searched in an entirely different direction. Instead of looking inward at psychology, they looked outward toward physics. They asked whether reality itself might have changed. Now, since CERN was conducting the most energetic particle collisions ever produced by human beings, it became the focus of speculation. And the timing seemed suspicious to some observers. Now, the Higgs boson had been discovered in 2012, and around that same period, discussions about the Mandela effect exploded across the internet. I remember it vividly. So, correct correlation quickly became, for many people, a suggestion of causation. Now, the idea that CERN had somehow fractured reality or shifted humanity into another timeline spread rapidly because it offered a dramatic explanation for an already mysterious phenomenon, the Mandela Effect. And one version of this theory became especially influential. It claimed that when protons collided inside the Large Hadron Collider, one proton was somehow displaced from its proper position in space-time. I mean, is that possible? I don't know. If you break one up or move it around, how is it really moving out of its own reality? Well, according to the story, this tiny disturbance cascaded through reality itself, shifting humanity into a neighboring timeline that differed only slightly from the original. Now, in this new reality, history remained almost identical, but small details have changed, like Mickey Mouse crap and other things, and the Berensteins and Bernstein and bears. Most people supposedly never noticed, while others retained memories from the previous timeline. Now, the Mandela Effect, according to this explanation, became evidence that reality had been altered rather than human memory. Okay? So as the story spread, new details were added. Some versions claimed CERN had accidentally opened a portal between universes. Others suggested the collider had weakened the barrier between parallel realities. Still, others argued that quantum mechanics predicted branching universes, and that CERN had somehow pushed humanity from one branch to another. Now, different storytellers borrowed ideas from particle physics, cosmology, science fiction, and quantum mechanics until they formed a single narrative that sounded scientific, even if many of its individual concepts came from very different areas of research. Surfer Wife says, hey, no, I never saw Tommy Boy and remember Darth Vader saying that. Well, I know we all have different memories of these things, and quite frankly, it's hard to get a straight answer here. So one name often associated with these discussions is Max Laufin, L-O-U-G-H-A-N, Laufin. I'm just going to say Laufin, sometimes described online as a child genius or physics prodigy. He's an adult now, but when he was a kid, they had a short video clip of him circulating widely in which he discussed the possibility that CERN's experiments had altered reality. Well, over time, countless videos, articles, and social media posts repeated or expanded upon these ideas. Now, as frequently happens on the internet, later versions often become more dramatic than the earliest ones, and claims that may have started as speculative questions gradually evolved into confident declarations that humanity had already crossed into another timeline. Well, unfortunately, as the story spread, references to published physics became increasingly rare, while repeated internet quotations became increasingly common. So this presents us with an important challenge and opportunity. It is very easy to dismiss extraordinary claims simply because they sound unusual. And it's equally easy to accept them because they are intriguing, which for a long time I was under the impression that CERN was changing reality, right? But when we do our homework and we really do some research, not all history books, not all scientific books, not all information out there is from the devil. But neither approach helps us discover the truth. Science has advanced many times by investigating ideas that initially sounded impossible. And at the same time, science also requires that every extraordinary claim be supported by evidence and by mechanisms that can be described mathematically or experimentally. Well, the proper response is neither ridicule nor blind belief. It's just investigation. And thanks to artificial intelligence, we can do more investigation now and find the truth quicker, faster, and move on to the next story. So before we ask whether CERN changed reality, we must first understand what CERN actually does. Before we ask whether timelines can shift, we must determine whether modern physics even contains a concept equivalent to what most people call a timeline. Now, before we evaluate claims about alternative realities, we must understand how physicists define space-time, quantum states, branching histories, and decoherence. They don't actually go watch Back to the Future and assume that that's how it really is. They don't. They actually have the mathematics to prove that whatever Doc Brown was working on wasn't really true. Only then can we actually fairly compare the internet's most popular theories against the best science currently available. And why shouldn't we do this? Surfer Wife says, so why do they want to do this? I think it has to do with us worshiping God and Jesus, but maybe reading too much into it. Well, I don't know. If I was Satan and I had the ability to get man to create some kind of a machine to change timelines, if there are timelines, I would try to find a timeline that doesn't have Jesus coming back. That's just me. By the end of tonight's investigation, we may conclude that the CERN timeline theory has no support in established physics. Aw, wah, wah. We may also discover that parts of it resemble legitimate scientific ideas, while other parts just do not. We may also uncover questions that physics itself has not yet answered. So whatever the outcome, our responsibility is the same. Follow the evidence wherever it leads. Separate observation from explanation. Refuse to accept conclusions simply because they are popular, and reject them simply because they are controversial. Okay? Our journey begins not with the alternative realities, but with a much simpler question. What actually happens when two protons collide? Huh, you ready to go? All right. Bruce here, he'd be like, this is what happens when worlds collide. I can't scream like that. Before we can decide whether CERN could have altered reality, we need to understand something much more basic. What actually happens inside the Large Hadron Collider? Well, surprisingly, many discussions about CERN begin with extraordinary conclusions without ever explaining the experiment itself. If we are going to test claims honestly, we must first understand what the machine is designed to do and why physicists built it in the first place. The Large Hadron Collider, or LHC, it's one of 3,000 that are out there right now. It's not the only one. It's just the largest. Is the largest and most powerful particle accelerator ever constructed that we know of. It sits beneath the border between Switzerland and France, where Satan is located, apparently. That's where his throne is, in a circular tunnel approximately 17 miles or 27 kilometers in circumference, underground. Thousands of superconducting magnets, huge ones, cooled to temperatures colder than outer space, guide beams of particles around this enormous ring. Now, these magnets do not create the particles. They simply steer and accelerate them with incredible precision towards each other. And every part of the machine exists for one purpose: to study matter at the smallest scales currently accessible to science. Makes sense. Watch them explode and see what they turn into. Find out if there's other particles inside the particle you're exploding. Now, the particles used most often in these experiments are protons, light. At first glance, that may not sound very exciting. Every atom of hydrogen contains a single proton, and every atom in your body contains protons inside its nucleus. Yet a proton is not a simple object. It is made of smaller particles called quarks, which are held together by particles known as gluons through the strong nuclear force. Well, inside every proton is a constant storm of energy and interactions. When physicists accelerate protons to nearly the speed of light, they are not trying to destroy matter. They are trying to expose what lies beneath its ordinary appearance. Now, one common misunderstanding is that the collider simply smashes solid balls together like two marbles colliding. Well, that's not exactly what happens. At the quantum level, particles behave very differently from objects in everyday life. They possess both particle-like and wave-like properties. And the outcome of the collision is described by probabilities rather than simple mechanical impacts. Now, when two protons beams cross inside one of CERN's detectors, countless interactions become possible. Most collisions are relatively ordinary by particle physics standards, and some produce familiar particles. Others briefly create particles that exist for only tiny fractions of a second before decaying into other forms of matter and energy. So after they hit, they fizzle out. Imagine watching two watches, with time on it, collide in midair, two Rolexes. If they struck one another at an ordinary speed, you might recover two damaged watches, maybe break the face of it. Now imagine they collide at an enormous energies that instead of broken watches, you briefly produce gears, springs, screws, tiny fragments, flashes of light, and entirely new pieces that never existed before the collision. Well, by examining those fragments, you can learn how the watches were built. And that is essentially what particle physicists do. Now you know. They are not interested in destroying protons. They are interested in studying the products that emerge when the proton's internal structure is revealed. And this is why CERN's detectors are so enormous. They have to be, because they've got to push those beams together to hit and collide. The detectors are not the collider itself. They are giant scientific cameras surrounding the collision points so they can film it. Every collision produces showers of particles flying outward in every direction, right? Sophisticated electronics record the paths, energies, charges, and lifetimes of these particles. And powerful computers then reconstruct what most likely happened during the collision, because we can't see it with the visible eye. So they are reconstructing events from enormous amounts of data using well-tested mathematical models and experimental measurements. Now, the discovery of the Higgs boson illustrates this process perfectly. Scientists never observed a tiny glowing particle floating from space. Instead, they detected the particles produced when the Higgs boson rapidly decayed into other particles. Those decay products matched predictions made decades earlier. So like detectives reconstructing a crime scene from fingerprints and footprints, physicists reconstructed the presence of the Higgs boson from the evidence it left behind. Now, the achievement was remarkable because the evidence agreed with theoretical predictions to the extraordinary degree. And also, if they're colliding and colliding protons together, like splitting the atom, if it was dangerous, the whole place would blow up, right? Well, this brings us to the first important question in our investigation. How much energy do these collisions actually involve? Well, news headlines often describe the Large Hadron Collider as producing unimaginable energies, scaring the crap out of you. And compared to previous laboratory experiments, that description is pretty accurate. Individual proton beams travel at more than 99.9999999% of the speed of light. And when they collide, they reach energies measured in trillions of electron volts. Well, to particle physicists, these are incredible energetic events. To everyday experience, the numbers sound almost impossible to comprehend. But it's at such a small scale that nobody talks about how small the explosion is. You don't even see it. In fact, protons are colliding all over the universe all the time. Speed of light hitting speed of light. They're exploding everywhere. We just decided to put it together into one place where we can observe it. That's what CERN is. There's another way to look at those same collisions, although the energy is enormous when concentrated into an object as small as a proton. The total amount of energy involved is surprisingly modest by everyday standards. A flying mosquito carries more total kinetic energy than a single proton collision. So we could probably get something even more out of colliding two mosquitoes together at the speed of light than we can out of these things. So the extraordinary achievement of the LHC is not that it produces vast amounts of energy overall, is that it concentrates energy into an unimaginably tiny volume for an unimaginable brief moment. Blink for a second, it's done. And that concentration also allows particles that normally cannot exist to appear briefly before disappearing again. And they've been trying to trap that energy, and they call that dark matter. Now, this distinction is critical because many internet discussions unintentionally confuse energy concentration with total energy. A lightning bolt releases vastly more total energy than a proton collision. A baseball pitch carries far more kinetic energy than an individual proton. What makes CERN unique is not the quantity of energy, but the density of energy of microscopic scales. Physicists are recreating conditions similar to those that existed shortly before or shortly after the Big Bang, but not by generating astronomical amounts of power, but by compressing relatively small amounts of energy into extremely small regions of space. And this is where scientists go, yeah, well, when you do that, you're messing up with space-time. Well, we haven't proved that there is a timeline and other timelines. So we arrive at the first serious challenge here is the timeline theory, and nature has been performing particle collisions for billions of years. One star, another star, sending light. These, at the speed of light, those protons will collide, one star and another. It happens. Throughout the universe, cosmic rays travel at extraordinary speeds, and some pass as energies that equal or even exceed those produced by the Large Hadron Collider. Every day, those cosmic rays strike Earth's atmosphere, colliding with atoms and producing cascades of secondary particles remarkably similar to those studied at CERN. Now, these natural experiments have occurred not merely thousands or millions of times, but countless of trillions upon trillions upon trillions of times throughout Earth's history. This is, on paper, it's mathematical. It's a reality. And they have also occurred across every star, galaxy, and region in interstellar space in the observable universe. We just didn't hone it down into one place we can take pictures of it and use computers to analyze it. Well, this observation does not automatically disprove the CERN hypothesis, but it does force us to ask better questions. If high-energy proton collisions are capable of shifting reality into another timeline, why has the universe not already experienced such shifts continuous for billions of years? Okay? One star, two star, lights going at each other. How come they're not creating new timelines? That's just common sense. So if high-energy proton collisions alone are capable of shifting reality, then why has the universe already experienced such shifts continuously for billions of years? And any theory proposing that CERN uniquely changed reality must explain why naturally occurring collisions of comparable or even greater energy have not obviously produced the same result. Well, that's a serious scientific challenge, and it does deserve an equal serious answer. Now, supporters of the timeline theory sometimes respond that CERN's collisions, well, they differ from cosmic rays because the beams are precisely controlled. And unlike random cosmic ray impacts, CERN accelerates two beams directly toward one another, producing head-on collisions under carefully engineered conditions. Well, this is an interesting observation, and it does deserve consideration rather than dismissal. The geometry of a collision can affect the amount of energy available in the collision itself. Now, whether that difference is enough to support claims about changing reality is another question entirely, but it is at least a meaningful scientific distinction that should be investigated rather than ignored. I don't know if you guys remember, but there was a bunch of scientists from Hawaii who sent letters to CERN saying, don't turn it on before 2012 because they were going to ruin the universe. That happened. Now, did it ruin the universe? Doesn't seem like it, but everyone thinks that we live in another reality because, well, they're starting to wake up to evil. This is the great awakening that happens before Jesus' return. So at this point, however, we have learned something important. Nothing that we have described so far requires alternative timelines, parallel universes, or shifts in reality. There's nowhere in CERN's paperwork that talks about that. And every collision observed at CERN is currently explained using the mathematical framework of quantum field theory and the standard model of particle physics. Now, the machine performs exactly the kind of experiments it was designed to perform. If something extraordinary occurred beyond those predictions, then we need to see some evidence that points beyond the known physics, not merely the fact that energetic collisions took place. Now, there are people that live above CERN, and they're having normal lives. Are you seeing videos saying, well, they turned on CERN today and I'm missing an arm, It's like, what's going on? I'm usually good at that, but sometimes they just make shirts and won't let you play the arm game. Well, that realization leads us to the next and perhaps most important question of the entire investigation. Everyone keeps talking about timelines, but what exactly is a timeline? Are they even real? Well, we saw it in Bill and Ted's Excellent Adventure. It's got to be. Stop. It may sound like a simple question, but we'll soon discover modern physics rarely uses that word at all. Instead, physicists speak of space-time world lines, quantum states, histories, decoherence, and branching. These concepts are related, but they are not identical. And before we can determine whether reality shifted, we must first determine whether science defines reality in the same way that popular culture does. Only then can we fairly test the extraordinary claim that CERN changed the world we live in. And don't put it past Satan to try. Absolutely 100%. And don't put it past CERN to have other experiments that they're doing without telling anybody on paper. It could happen. But I don't think it's happening at CERN. I really don't. I think if it's happening somewhere else, some military base, not in public view. We've now reached the point where most discussions about CERN begin to fall apart. Not because the questions are foolish, but because the language becomes imprecise. Ask 10 people what a timeline is, and you'll probably receive 10 different answers. Some imagine a straight line of history stretching from the past into the future. Others picture parallel universes existing side by side. Some think of alternative realities that branch every time a decision is made. Still, others imagine entirely separate dimensions. Well, the problem is that modern physics does not use these ideas interchangeably. In fact, physicists rarely use the word timeline at all. Now, if we want to investigate this honestly, we got to first understand the vocabulary that physics actually uses. Let's begin with something familiar: space-time. Are there many space-times? They don't think so. Before Albert Einstein developed his theory of relativity, most scientists thought of space and time as separate things. Space was the stage on which events happened, and time was the clock that measured them. Well, Einstein showed that this picture was incomplete. Space and time are woven together into a single four-dimensional structure called space-time. Now, every event that has ever happened, every event happening now, and every event that will happen occupies a particular location within that structure. When physicists calculate the motion of planets, stars, or even particles, they describe events, or those events, as taking place within space-time, not timelines. Inside space-time, every object traces what physicists call a world line. Now imagine watching an airplane fly across the sky. If you could leave a glowing trail behind it, that trail would show where the airplane had been, like a chemtrail. Now imagine adding the passage of time as another dimension. Instead of a simple path through space, the airplane would leave behind a path through space-time. Well, that path is called its world line. Every person has one. Every planet has one. Every photon has one. Every photon traveling through the Hadron Collider has one. And notice something important already. A world line is not the same thing as what people usually mean by a timeline. A world line belongs to an individual object moving through space-time. It is not an alternative history, meaning it's just a trail that's left after it moved from A to B. Now we move into quantum mechanics, where the language becomes even more unfamiliar. Instead of describing particles as tiny balls with exact positions and velocities, quantum mechanics describes them using something called the quantum state. The quantum state is not simply a list of where particles are located. It is a mathematical description containing all of the information needed to calculate the probabilities of future observations. Now, different interpretations of quantum mechanics disagree about what the quantum state actually represents, but they all use the same mathematics. Now, this distinction is crucial because many internet discussions unknowingly mix mathematical descriptions with philosophical interpretations. And one of the greatest mysteries in quantum mechanics is known as the measurement problem. We've got a problem here. Well, at the microscopic level, quantum systems evolve smoothly according to mathematical equations. Yet when measurements are made, we observe definite outcomes. Okay? How does one become the other? Well, physicists have debated this question for nearly 100 years. They haven't come to a conclusion yet. Some interpretations propose that the wave function somehow collapses during measurement. Others argue that the collapse never occurs at all. Well, this agreement is not a fringe discussion. It lies at the heart of one of the deepest unresolved questions in modern physics today, in 2026. And this is where Hugh Everett enters the story. In 1957, Everett, a scientist, proposed a radical solution that eventually became known as the many worlds interpretation. Oh, shit. Here we go. Timelines. Instead of assuming the wave function collapses into a single outcome, Everett suggested taking the mathematics literally, which sometimes you should. According to this view, the quantum state continues evolving without interruption. What appears to us as a single outcome is actually part of a much larger quantum reality. And over time, different components of that quantum state become effectively independent through a process called decoherence. Now, David Wallace, another scientist, one of the leading modern defenders of Everett's interpretation, well, he argues that what we call separate worlds emerged naturally from this process rather than being created by mysterious universe-splitting events. Well, notice what's happened. The internet says, or often says, timeline. Everett says branch. Well, those are not automatically the same thing. They're different things. A branch in Everett's framework is not another universe floating beside ours like another planet in space. It is a description of how different components of the quantum state evolve so that they no longer interfere with one another. Well, these branches emerge continuously through interactions with the surrounding environment. They are not opened like doors. Timelines. Branches. They are not created by machines. They are consequences of how the mathematics evolves if one accepts Everett's interpretation, which it's a theory. That's a very different picture from the one commonly presented online. Oh my God, we got other timelines. I'm in a new timeline, and this one, I'm just really, really horny. No, you're just not. Get back to the Bible. The key word here is decoherence, because it may be the single most misunderstood concept in the entire discussion. Imagine dropping two stones into a perfectly calm pond. Now, at first, the ripples overlap and interfere with one another. Okay, you can clearly see their combined pattern. Now imagine the pond becoming increasingly rough as wind, rain, and countless disturbances just suddenly appear. Very quickly, those original ripples become impossible to distinguish from everything else that's happening on the surface. It's chaos. They have not disappeared. They have become actually ineffectively impossible to observe separately. Well, decoherence works in somewhat a similar way. Quantum systems constantly interact with their environment, and those interactions rapidly destroy the interference needed to observe certain quantum behaviors at everyday scales. Well, the result is that the world appears classical, even though its underlying description remains quantum. So this has profound implications for the CERN hypothesis. If Everett and Wallace are correct, branching is not a rare event waiting for a giant particle accelerator to trigger. Branching would occur continuously throughout the universe as quantum systems interact with their environments. That means every proton striking your eyeball, every atom vibrating inside a crystal, every molecule colliding in the atmosphere would participate in this ongoing process of decoherence. CERN would not create branching. At most, it would provide another example of quantum systems evolving according to the same fundamental principles already operating everywhere else in nature. So another word frequently used in discussions of CERN is parallel universe. Timelines, parallel universes. Dude, this universe isn't the only one. There's endless. It's endless. It's anarchy. Well, here again, precision matters. Cosmologists use the term in several completely different ways. Some refer to regions beyond our observable universe created during cosmic inflation. Others discuss higher dimensional brain world, which is B-R-A-N-E, not brain world. These are models arising from string theory, and still others refer to Everettian branches, Everett and his branches theory with quantum mechanics. Well, these ideas all involve more than one world, but they are based on entirely different mathematical frameworks. Saying a parallel universe without specifying which theory is being discussed is like saying vehicle without telling whether you mean it's a bicycle, an airplane, or a submarine. So the word alone is simply too broad to answer serious scientific questions. And like everything, there's always a spectrum. There's more to the story. Well, this realization may be the most important discovery that we have made so far. When someone says CERN moved us into another timeline, what do they actually mean? Do they mean another world line? Do they mean the Everest branch? Do they mean another space-time? Do they mean another universe created during inflation? Do they mean another higher dimensional brain, B-R-A-N-E, or another quantum history? Well, each possibility belongs to different area of physics. Each has different mathematical foundations. Each makes different predictions. Until those distinctions are actually made, the conversation cannot move beyond speculation because the central claim has never been clearly defined. And there's another subtle point that often goes unnoticed here in the CERN debate. Throughout all of my research, I found extensive discussions about branching, decoherence, quantum histories, and space-time. What I did not find was an accepted physical quantity that could be described as a particle's timeline position. Physicists calculate position, momentum, spin, charge, mass, energy, and quantum states. But they do not calculate a particle's location within a timeline because no such quantity exists in the standard model of particle physics. So that does not prove such a concept could never exist in a future theory, but it does not mean that claims involving a proton being knocked out of our timeline requires definitions that current physicists simply does not provide. Physics doesn't provide that. The mathematics isn't there. So we're no longer asking whether CERN changed timelines now. We're asking whether the concept that people associate with timelines correspond to anything that modern physics actually predicts. Well, physicists are laughing at us dummies who fall for everything that we read and see and hear. So that is a far more precise question here, and one that deserves careful examination rather than a quick conclusion. But now that we understand the language of space-time, world lines, quantum states, branching, and decoherence, well, we can finally investigate the interpretation most often cited in support of alternative realities. It is time to meet the man whose ideas transformed one of physics' greatest mysteries into one of the most controversial possibilities. And who was Hugh Everett? And did he really discover many worlds? Well, in 1957, a young graduate student named Hugh Everett III, submitted a doctoral thesis that challenged one of the deepest assumptions in all of physics. Now, at the time, most physicists accepted what is commonly called the Copenhagen interpretation of quantum mechanics. Now, according to that view, the mathematical descriptions of a quantum system evolves smoothly until a measurement is made. Well, at that moment, the wave function is said to collapse into a single outcome. We've talked about wave function before. Now, the mathematics predicts several possible results, but observations reveal only one. Now, for decades, this idea dominated physics classrooms all around the world. Yet there was one problem. They never completely disappeared. No one could explain exactly what qualified as a measurement or why nature should suddenly change its behavior simply because of an observation occurred. Well, Everett believed there was a simpler solution. Instead of changing the mathematics, he proposed changing our interpretation of it. What if the wave function never collapses at all? What if the equations of quantum mechanics describe reality exactly as they are written? Rather than assuming that one possibility becomes real while every other possibility vanishes, Everett suggests that every outcome described by mathematics continues to exist within the evolving quantum state. So his proposal was radical because it removed collapse entirely. So the equations no longer required a mysterious exception during measurements. They simply continued evolving according to the same rules at every scale. Now, at first, Everett's work received little enthusiasm because they thought he was nuts. Even his advisor, the famous physicist John Wheeler, encouraged him to soften some of the more controversial implications before publishing his dissertation. Many physicists viewed the idea as philosophically extravagant, and in every possible outcome continued to exist. Now, that did not mean reality constantly multiplied into countless worlds. The proposal sounded more like science fiction than science, and Everett eventually left academic physics, and for many years his interpretation remained on the fringes of scientific discussion. Why did he leave? Yet the mathematics itself never disappeared, and over time, a growing number of physicists began revisiting his ideas. And one of the most important figures in that revival is David Wallace. In his book, The Emergent Multiverse. It's not a popular science book written to entertain general audiences. It's a detailed technical defense of Everett's interpretation aimed at physicists and philosophers of science. Now, Wallace argues that Everett's approach should not be viewed as adding imaginary worlds to physics. Instead, he argues that if quantum mechanics is taken literally, branching worlds naturally emerge from the mathematics through the process of decoherence. In other words, the branches are not extra assumptions added to quantum mechanics. They are what Wallace believes the mathematics already describes if we stop forcing it to collapse. Now, this is an important distinction because it actually changes the entire conversation, okay? Towards is CERN really changing the timelines. Now, notice what Wallace is not saying. He's not saying that universes are constantly popping into existence like bubbles. He's not saying that portals open between realities. He's not saying he's opening hell. He's not saying that giant machines create alternative worlds. Instead, he just argues that what we perceive as a single classical world is only one stable pattern emerging from a much larger quantum description of reality. So according to his view, branching is not an event that occasionally happens. It's a continuous consequence of quantum evolution itself. And that is far more subtle claim than the internet often presents. Okay, so what he's trying to say is, no, there's no multi-other worlds. There's no a billion of you making choices and creating your own alternative reality because you chose something that you weren't supposed to choose. He just says, hey, we're changing it as we go. And my theory says the evidence is left through the cohort. What is that called again? Decoherence. Okay? Does that make sense? So to understand this idea, imagine standing at the trunk of a massive oak tree. As you look upward, the trunk divides into large branches. Those branches divide into smaller ones, and those smaller branches continue dividing until thousands of twigs reach toward the sky. Now imagine that the trunk represents the quantum state of the universe. The branches do not suddenly appear because someone built a machine. They emerge naturally as the tree grows, and Everett's interpretation suggests something similar. The quantum state evolves continuously, and what we experience as classical reality corresponds to one of many branches that become effectively independent through decoherence. All right. So this is where many online discussions unintentionally oversimplify the science. They often describe the many worlds interpretation as though every decision instantly creates a brand new universe or a new branch. Well, that's a different reality. Well, while that image is useful for introducing the idea, it's not how modern defenders like Wallace usually describe the mathematics. They emphasize emergence rather than duplication. A branch is not necessarily a separate universe floating beside ours. It is an effectively independent history arising from the quantum state because interference between different components has become negligible. Now, whether one wishes to call those branches separate worlds becomes partly a matter of interpretation, but the underlying mathematics remains the same. And his predecessor said they're not different worlds. So another misconception deserves attention, and many people imagine that if branches exist, then traveling between them should be possible. Yet Everett's interpretation does not provide such a mechanism. In fact, the opposite is generally true. Once decoherence has occurred, branches become effectively isolated from one another. They no longer exchange information in any meaningful way. They no longer interface as they did before decoherence. And from the perspective of observers within one branch, the others become inaccessible. Well, this is one of the reasons that many physicists argue that Everett's interpretation, while mathematically elegant, is difficult to test experimentally. And if the branches cannot interact, how would observers ever compare them? Well, this is a problem. And this point has enormous consequences for the CERN timeline theory. Okay, if Everett is correct, branching would not require Large Hadron Collider. It would not begin in 2012. It would not depend upon the Higgs boson. It would not require a single proton to be displaced from anything. Branching would already be occurring continuously throughout the universe, whether quantum systems interact with the environments or not. Every atom, every molecule, every photon, and every particle collision would already participate in this ongoing process. CERN would simply be another place where quantum mechanics is being studied under carefully controlled conditions. So some supporters of the timeline theory might respond to that while branching occurs everywhere. And CERN somehow produced an unusual significant branch because of the enormous energies involved. Well, that's a reasonable question to ask, but notice how different it is from the original claim. We've already moved away from saying that CERN created alternative timelines. Now we're asking whether exceptionally energetic quantum interactions could influence branching in unusual ways. And that is a much more precise scientific question, and it's one that can actually be investigated. And it may ultimately prove false, but at least it belongs to the language of physics rather than the language of internet folklore, which everyone's falling for, I believe. Now, another interesting aspect of Wallace's work is his emphasis on decoherence rather than observation. Older popular descriptions of quantum mechanics often suggested that consciousness somehow caused the wave function to collapse. Remember, we talked about throw two pebbles into the water, and then you'll see two different waves, and then all of a sudden a bunch of shit comes in, like storms and stuff, weather, and now you can't tell what's what. Well, this led to countless claims that human thought actually creates reality, or that observation magically changes the universe. What the hell was that? I always get weird noises. Oh, it was a train. In his framework, decoherence results from ordinary physical interactions with the environment and not from conscious observers. Now, the universe does not wait for someone to look before deciding what is real. Physical systems interact continuously whether anyone is watching or not, and that shift removes much of the mystical language that has accumulated around quantum mechanics over the past century. Now, this also means that many internet explanations combining consciousness, CERN, and timeline changes may be blending together ideas that originate from entirely different interpretations of quantum mechanics. Some discussions unknowingly mix Copenhagen, Everett, conscious-based interpretation, simulation theory, and science fiction all into a single narrative. Well, that doesn't explain what's happening. It's all mixing together, and that's not logical. And once these ideas are separated, it becomes clear that they're often answering different questions using different assumptions. And simply invoking quantum mechanics, that does not automatically connect them into one coherent theory. It could be just simple physics. It could be creating a branch like they're talking about, but it's separate from our own reality. And by now, one thing should be becoming clear is that Everett's interpretation is far stranger than most people actually realize, but it's also far more disciplined than popular presentations suggest today. Meaning CERN could be creating another branch, but that still, and somehow that branch is bleeding into our existence, but that branch is still part of the tree. And that would not explain the Mandela Effect. Now, it does not claim that particle accelerators open doors into neighboring realities. Instead, it offers a mathematical, consistent way of understanding quantum mechanics without invoking wave function collapse. Whether that interpretation is ultimately correct remains one of the greatest debates in modern physics today, but it deserves to be understood on its own terms rather than through internet summaries, which we all seem to think is real. Everything we see, read, touch, feel is real. Well, you got to use discernment. At this stage in our investigation, we've learned something unexpected. The strongest scientific argument connected to alternative realities actually weakens one of the central claims of the CERN timeline theory. I know, this is heavy shit. I get it. But it's the only way I can explain quantum mechanics, physics altogether, and basically saying that what CERN is doing is not what we think it's doing. It's not creating the Mandela Effect. But if it's doing anything, it could be a theory from Everett and his work, and Wallace and his following work of Everett, that they could be creating branches. But even that is so stretching because of just one proton hitting another proton, how does that change an entire universe? Could anything about the Large Hadron make its branching fundamentally different from the branching that would already be occurring everywhere else in the universe? No, because it's already happening in the universe. So thus, many branching would be occurring, and there would be many things bleeding into another, and the Mandela Effect would be something as normal as finding the same effect in books in the 1700s of people remembering events differently. So that's a question that we're going to examine next. It finally allows us to test the central hypothesis against the actual mathematics of quantum physics, rather than against the speculation alone. So at first glance, the answer appears obvious. CERN performs the most energetic controlled particle collisions ever created by human beings. Okay, and these particle acceleration hitting happens in the universe all the time. Okay, CERN performs the most energetic controlled particle collisions ever created, and the energies involved are so extraordinary that physicists can briefly recreate conditions that existed fractions of a second after the Big Bang. Now, it's understandable why many people would wonder whether such an experiment might uncover something entirely new. Throughout history, whenever humanity has reached a new frontier, whether sailing across oceans, splitting the atom, or exploring space, we've discovered things that no one expected. It's not unreasonable to ask whether particle physics might eventually reveal surprises as well. And what if the simplest answer is this, that the Large Hadron Collider has been creating gold using lead by smashing lead together? And it takes a long time to create lead into gold, and they got to make it even bigger because, well, countries are competing against gold. The West is in control of the Large Hadron Collider, and the East is creating them as well. China is already building a Hadron Collider the size of the LHC currently. Are they all competing, just trying to, and they're just saying, well, the original thought was the Higgs boson, but really they're just creating gold? I think it's the latter. So to answer our question, honestly, we need to distinguish between two completely different ideas here. The first asks whether CERN could discover new physics. It did. Almost every physicist would answer yes, and in fact, that's one of the primary reasons the collider exists. And look, you're not going to spend billions of dollars just to find a freaking particle, okay? They're spending billions of dollars to make something back, okay? That's a business. All right. Nobody throws money at science and hoping that they can get a patent and actually make money off of it. No, it doesn't work that way. It has to be proven and ready to go. And they have to present a business plan that shows them when they're going to make their return on their investment. Otherwise, so the Large Hadron Collider and all the other colliders, what they're really for, I think they're just for making gold, because we need a lot of it. Because we're making computers, and computers need a lot of it, and we just don't have the time to dig it out of all these crevices, because it's a pain in the ass, speaking of a gold miner myself. Scientists hope to find evidence of particles or interactions that extend beyond the standard model, and the second question asks whether CERN could fundamentally change the structure of reality itself. Well, that's a much stronger claim, and it requires a mechanism that current physics can describe. And the difference between discussing something new and altering reality is enormous. And one reason the timeline theory became so persuasive online is that people often assume high energy automatically means high danger. Well, that assumption feels intuitive because it matches our everyday experience. Explosions become more destructive as their energy increases, and powerful storms produce greater damage than gentle breezes. Yet particle physics operates on scales that are difficult to compare with ordinary life. You can't see it. It explodes, and you can't even see it explode. And if it had a cascading effect where it would just continue to explode everything else, it would have, if they would have turned it on, it would have blown everything up. You see, a proton collision concentrates tremendous energy into an unimaginably tiny region for an unimaginably brief moment. The total energy involved remains remarkably small. So what matters is not how much energy exists overall, but how densely it's concentrated. Now, if you were living on a planet that orbited that proton, that you were tiny. You're really tiny. That orbited that proton, which just so happened to be the sun in your galaxy or in your planetary system. And they shot you, and they shot you against another sun with planets. Yeah, you're screwed. And yes, you could feel that energy. It would be big time if you were that tiny. We're talking such a tiny, 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 tiny thing that we can't even possibly imagine because we still can't see it visibly yet. Now, suppose someone claims that this extraordinary concentration allows CERN to reach parts of reality that nature cannot. Well, that sounds plausible until we remember something from the previous chapter that we talked about. Nature has been accelerating particles to extraordinary energies long before human civilization existed. It's been doing it. And according to Wallace's work on Everett, it's all those branches are branching. It's happening all around us. And some originate from exploding stars, active galaxies, and other violent astrophysical events whose energies exceed those produced inside the Large Hadron Collider. Yeah, if they were really tiny. Well, these natural particle accelerators have been operating continuously for billions of years. If concentrated energy alone changes reality, then nature has been running similar experiments throughout the observable universe since long before the first human looked at the stars. And supporters of the CERN hypothesis sometimes answer this objective by pointing out an important difference. They say cosmic rays usually strike stationary atoms, while CERN accelerates two beams directly toward one another. Well, that distinction is scientifically meaningful because head-on collisions make more energy available in the center of mass where new particles can be produced. So in other words, CERN uses energy more efficiently than many naturally occurring collisions. This is one of the reasons the Hadron Collider was built in the first place. Rather than just simply creating higher energies, it creates cleaner and more controllable experimental conditions. So could controlled collisions produce effects that random cosmic rays do not? Well, that's the kind of question scientists ask every day. Yet even if the answer were yes, it would not automatically support the timeline theory. It would simply mean CERN can study certain particle interactions more effectively than nature usually does in Earth's atmosphere. Look, I want this to be true, just like you guys do. And every time I really do hard research and I bring together as many books as I possibly can and every internet article and journal I can find and every published paper, I put it all together and I get disappointed. The conspiracy theories to get us afraid is all a bunch of bullshit. No such mechanism has been demonstrated experimentally yet that changes anything when it comes to smashing particles together. But if we return to Everett's interpretation, if Wallace is correct, and these branchings is not triggered by unusual events, then branching is simply the natural consequence of quantum evolution together with decoherence. Every interaction between quantum systems and their environment contributes to this ongoing process. The Large Hadron Collider does not operate outside quantum mechanics. It operates in mathematics. It operates entirely with quantum mechanics, and every magnet guiding the beams, every detector recording particle tracks, every computer analyzing collision data, all of these are themselves quantum systems. And nothing inside CERN escapes the laws governing the rest of the universe. CERN is not going to open up a portal to hell. It's just not opening up anything. It's just smashing particles together. Now, that doesn't mean that they don't have other things that could do that. Sure. I'm just saying what CERN is doing on paper doesn't seem like they're up to anything but, in my opinion, making gold. Because that's how you make gold, is by splicing lead together. And sure, on the side, they'll do these other experiments. Yeah, just to please the scientists, but I think they're making gold. It's the simplest explanation for why they would spend billions and then want to upgrade it to 3 times its size now. Nothing inside CERN escapes the laws governing the rest of the universe, okay? It's not like they built something that is so extraordinary that it will collapse the universe inside a black hole. No, we're giving them way too much credit, and they're loving it because they want these kinds of uh, things going on. Because you know what? While they're stealing your money through making new laws that take away more of your freedom, these little stories of Mandela Effect and changing timelines and intergalactic space brothers living on Saturn, fighting the reptilians, all that shit makes you continue to not research what they're doing and hold them accountable to their theft. Sorry. I just don't think I don't think that CERN is what people claim it is, especially after going through all this information. It sucks, I know. Every time I do research on a topic that I know, that I really feel like I know in my heart that this is Satan's plan to destroy the world, I get let down every time. So could we ever cross between branches? Okay. Wallace says no. Everett says no. But up to this point, we've asked whether the Large Hadron Collider could create or influence a branch of reality. Well, this is even a more important question. Even if branching exists, which has not been fully accepted yet, could anyone ever move from one branch to another? Well, this question lies at the heart of nearly every timeline theory on the internet. And it's one thing to propose that reality branches. It's another to claim that human beings or even a single proton can cross from one branch into another. And surprisingly, these are not the same problem. The modern physics treats them differently. Imagine driving down a highway and suddenly it divides into two separate roads. And instead, once the roads split, each continues in its own direction. Cars on one road no longer interact with cars on the other unless someone builds a bridge connecting them again. Well, Everett's interpretation describes branching in a remarkably similar way. Before decoherence, different quantum possibilities can interfere with one another. And after decoherence, they become effectively independent and they continue evolving according to the same laws of physics, but they no longer exchange information. So in that sense, the branch resembles highways that have permanently diverged, but you can see it, but you can't go into it. And this is why the word decoherence matters so much. Earlier, we described it as a process by which interactions with the environment suppress quantum interference. All the information after we drop two pebbles into the water and then nature hits and then the whole, earthquakes and storms and water, you can't, and all you were doing is tracking the two pebbles. It's chaos. So now we can see that suppression is so important. Decoherence is not merely a mathematical convenience. It explains why the everyday world appears stable and classical, even though its underlying description remains quantum. And once decoherence has taken place, the different branch ceases to behave as though they are part of a single observable system. So from the perspective of observers living within one branch, the others become ineffectively inaccessible. You just can't go into another. And notice what that means. If Everett's interpretation is correct, which 90% of the scientists who read his stuff say he's not, that's just a theory. The branching alone does not predict travel between branches. We can't. Now, remember that highway goes off into two and then they create a bridge to put them together, okay? Every time when CERN turns on, could it create a bridge? Yeah, but it's just a bridge and it looks like you get in there, but nobody can drive. So basically you're forced to drive past it. You can look at it. That's a bridge that goes in, but you'll never be able to get inside. Get onto the other highway that's split into two. Because mathematics predicts the opposite. The branches separate because interference disappears. Now, that separation is one of the very reasons classical reality emerges in the first place. If branches constantly reconnected, the stable world we experience would become extraordinarily difficult to explain. Instead of seeing well-defined objects, we would expect bizarre interference effects to appear everywhere around us. And fortunately for everyday life, they do not. So this creates a major obstacle for CERN's timeline theory and branching and Everett. That's the only possible way we could get the Mandela effect. But the moment we see the road, which are the two pebbles and the lines, the timelines, the branch to go into it, all hell breaks loose, and we can't see it anymore. We will not be able to read that data or put our hand through. Now, the theory usually assumes two things happened simultaneously. First, reality branched or shifted. Second, millions of people somehow carried memories from one branch into another, while physical evidence reflected only the new history. Well, these are actually two completely different claims. Everett addresses the first. He does not provide a mechanism for the second. And the theory would therefore require an additional process beyond ordinary branching, one capable of transferring information, memory, or observers across branches after decoherence had already separated them. So could such a mechanism exist? Well, the honest answer is that no accepted theory currently provides one. So no, science can't back up Everett and his timeline or world line theory of different realities that branch off due to decoherence. Now, the strongest arguments against the timeline theory. Well, the first objection is perhaps the most powerful of all. Nature has been running particle accelerators for billions of years. We can all agree on that. Long before human beings built the Large Hadron Collider, the universe was already producing particles with astonishing energies, smashing them together because when light hits light, okay, one star, other star, if they can see each other, they're sending protons at the speed of light, folks. Because light travels at the speed of light. So they're hitting and they're gonna hit. Okay? Cosmic rays travel across space at nearly the speed of light before colliding with planets, stars, gas clouds, and one another. And some originate from exploding stars known as a supernova. Others may come from active galaxies whose essential black holes accelerate matter to extraordinary speeds. Well, every second of every day, Earth is bombarded by these particles, and many carry energies that equal or even exceed these produced inside CERN. Now, supporters of the timeline theory sometimes answer that CERN's collisions differ because they're controlled. Well, we mentioned earlier that that's not possible. And in fact, it's what we're producing is far less than what's actually being produced in outer space every day. The second objection comes from the laws of conservation. Modern physics is built upon principles that have survived countless experimental tests. We can't experiment, Everett and Wallace. And energy, we know, is conserved. Momentum is conserved. Electric charge is conserved. Now, these conservation laws are not arbitrary rules. They emerge from deep mathematical symmetries within nature. And whether physicists analyze particle collisions or they carefully account for every measurable quantity entering and leaving the interaction, well, occasionally these particles seem to disappear. How? Well, not because they transform into other particles or forms of energies that detectors eventually identify, as nothing in the standard model allows an ordinary proton simply to leave our universe or slip outside space-time while preserving the mathematical consistency of the conservation laws. So, if you move a proton from here over to here, it's not going to change anything other than the proton is going to be here or there. If you break a proton in half or split it up into a million pieces, it's not going to change because it happens all throughout the universe on a daily basis. And we see it because when we look up into the sky, we see stars, and those stars those stars are pointing that energy to other stars, so they're all seeing each other. The next objection comes from experimental evidence, or more precisely, the absence of it. The Large Hadron Collider has produced an extraordinary amount of data over the years. And physicists have identified the Higgs boson, studied countless particle interactions, and tested the standard model with remarkable precision. And they continue searching for signs of supersymmetry, dark matter candidates, extra dimensions, and other new physics. Now, so far, however, no published experimental result indicates that collisions have altered space-time, transferred matter between quantum branches, or produced observable effects resembling timeline changes. Now, this does not prove that future discoveries are impossible. It just simply means that the evidence currently available does not point in that direction. Sorry. Now, after spending considerable time examining the strongest scientific objections, folks, it would be easy to conclude that the investigation is finished, but that would not be an honest investigation. Throughout the history of science, many accepted theories eventually proved incomplete. Newton's laws explained gravity with extraordinary accuracy until Einstein revealed that gravity was not a force acting across empty space, but a consequence of curved space-time. So what I'm saying is, science can be wrong. Science could miss a little detail that all the current scientists together and all their books and all their knowledge just couldn't put together, that maybe there is a possibility that the branches mentioned from Everett could somehow merge together. Well, today, there's no physical evidence of it. Today, Everest is still a quack. I'm serious. So what we really need to leave here with is simple intellectual humility, okay? What they're doing at CERN and what they published says that that's really not what's going on. If they're doing something underneath all of the paperwork and all the money is being supported, I would think it would have to do with making money versus science. They've already found what they needed. Why are they going more? Well, what do they need to break up now? What do they need to a more thinner beam of something else, or they just need to produce more gold? See, I came up with a theory, and this is just a theory, that every moon landing, every moon lander came down. It was wrapped in gold, and that machine that was wrapped in gold sits above all. And that's kind of mankind's way of saying, we control gold, now we can make it. And we've been splitting particles and accelerators since the 60s. So that's what I think that was about. And then later, India figured it out. Later, China figured it out. Later, Russia figured it out. And they too wrapped their lunar modules in gold. Just sheets, gold sheets, just thin. That's what they're making up there. Not up there, but in CERN. Just thin and tiny elements. And it takes time. And they need more. They don't have enough. We know how to create gold out of lead. Okay? We don't have to use alchemy and all of this, satanic mixture of goat's blood. We don't need any of that shit anymore. We can now just create gold. Now, throughout history, many scientific discoveries began because someone refused to dismiss an uncomfortable question. Because asking difficult questions is not anti-science, and refusing to ask them would be, right? The important distinction is how those questions are investigated. Now, it doesn't ask us to suppress imagination. It does ask us to test our imagination against reality. And the idea that quantum mechanics forces us to rethink our intuitive understanding of reality is unquestionably true. People who insist strange observations should be ignored because they did not fit existing theories have often delayed genuine breakthroughs. So we can't just dismiss the Mandela Effect. We can't just dismiss Everett's branching. We can't dismiss all of that. when it comes to the future. And there's going to be many discussions and many follow-ups and many articles in the next 20 years that may introduce a new theory based off of Everett's principles that they did somehow create branches. But as far as timelines are concerned, there's no such thing. And it doesn't prove it in physics or quantum mechanics. As far as other worlds, we've only come close through the work of Everett and his predecessor Wallace. But it's still not testable. We have not figured out a way to test it. And that is a big roadblock for what's going on. But curiosity without discipline easily becomes speculation. And that's perhaps why theories like this continue to capture the imagination. It captured mine anyway. I'm sure it captured yours. Real investigation demands both courage and humility, folks, and courage to question what everyone else assumes, and humility to admit when the evidence leads somewhere unexpected. Here at Cause Before Symptom, that has always been my mission. I don't chase the most exciting explanation. I chase the one that best fits the evidence. And sometimes the evidence confirms what I expected. Sometimes. And sometimes it surprises the crap out of me. Sometimes. But either way, truth is never harmed by honest investigation. And so far, I want to believe in the Mandela Effect. I want to believe that CERN's changing the timelines because it just sounds so fun. But reality does not change to match our theories. Our theories must change to match reality.
This has been Cause Before Symptom with your host, James Carner. Go to his website, jamescarner.com, and sign up for his newsletter. Also, download his free books, The Breath War, The Ritual Machine, The Crown of Blood, The Stone That Speaks, and The Crown of Cain. Oh, and one more thing. If you could just try and love your neighbor, we believe the world would be a better place. See you tomorrow.